Hello dear students. So in this last lecture before MST, we will just discuss a little topic which is Poisson distribution. Poisson distribution. So you see we are doing our 5th chapter where we have discussed about discrete probability distributions. So this is the distribution which was left. So let us discuss it. So what is a Poisson experiment? So Poisson experiment is basically when you count the number of outcomes occurring in a given time. For example, if you count number of outcomes occurring in a given interval of time, for example, maybe you are counting a number of telephone calls per day for an office, or you may say number of days school was closed due to snow per month in winters. Okay, so here you see what you are counting. If you look at the first example, here you are counting the number of calls per day for a particular office, and in the second event you are counting the number of days the school was closed due to snow per month in winters, right? Or you can have a situation like this. Suppose you are counting the number of mice per acre in a field. Okay, so here we were talking about time. We can also talk about number of outcomes okay, in an area, right? For example, we may talk about number of field mice per acre, or we can talk about number of mistakes, grammatical or any typos per page of a book, right? Things like this, they will be are called Poisson experiment. When you are measuring things like this, they are called a Poisson experiment, right? But still there are some conditions for the above process to be Poisson experiment. For the above process to be a Poisson experiment, we put the following conditions. The following conditions are to be met. So what are the conditions? So the first condition is the number of outcomes occurring in one time interval should be independent of what is happening in any other disjoint time interval. The number of outcomes occurring in one time interval, or we can talk about region also, one time interval or specified region should be independent of the number that occurs in any disjoint time interval or region, in any other disjoint time interval or region. So it means that what we are saying here, suppose this is my time interval, this is the timeline, and whatever is happening in this part, right, like how many number of outcomes are there in this part is independent of what is happening in some other region, other area which is independent, okay, which is disjoint. Is that That makes sense, right? So this way we say that the Poisson process has no memory. So this, we say that, like for this we say that Poisson process has no memory. Okay, why no memory? Because suppose like, because they don't know, the Poisson process doesn't know that, okay, what is happening here, that information is not passed here. So that is when you don't have any memory. Okay, so it's like that. So that should be there. So it's like independence. We had independent binomial trials. So this is the same thing, that we want independence, but because we have, here this time interval is a continuous thing, right? So we don't have discrete trials, we have continuous time, but in that continuous time we are counting the number of something. So the final variable is discrete, but the timeline is a continuous timeline, right? So we can't say that the first trial is independent of second trial. So we will say that whatever will happen in this interval is independent of what happens in some other interval which is disjoint. Okay, yeah. And then we also have the second condition, that probability that a single outcome will occur during a very short time. Okay, probability that a single outcome will occur during a very short time interval, or very small region is proportional to the length of the time interval, or size of the region is proportional to the length of the time interval, or the area or volume, whatever size of the region. Okay, it depends. If you're talking about a 2D area, will take areas, 2D region you will take areas, 3D region you will take volumes. Okay, and then the third thing is the probability that more than one outcome will occur in such a short time interval or fall in such a small region is negligible. So that means we can always, if you have a region, we can always have very small parts, so that the probability that more than two outcomes occur in that small part is negligible. Okay, so the probability that more than one outcome will occur in such a small or short time interval, or fall in such a small region is negligible. Okay, so these are the conditions for your process to be the Poisson process. Is that okay? So we have this situation that we are counting, what is our experiment? We are counting the number of outcomes occurring in a given time interval or in a given area, which satisfy the first property of independence. Second property, that probability of a single outcome for a small time will be proportional to the length of that interval. And third, that probability of two outcomes in very small interval is almost negligible. Then we call above process as a Poisson process, and x, which is number of outcomes in a given time t is called a Poisson random variable. And you should understand this is a discrete random variable. Because it measures the number of number of calls, number of errors, number of people, number of cars, something like that. So it is measuring number, so its value will be 1, 2, 3, 4, 5, 6. So it is not a continuous random variable. Okay, so x can be So this capital X can assume 0, 1, 2, 3 and so on. These values this capital X can assume. So it turns out that if lambda is the average number of outcomes per unit time, is average number of outcomes per unit time, then PDF, that probability that capital X is equal to X, that means X number of outcomes will occur in T time, okay, will be equal to, we denote it as P stands for Poisson, right, and then you have X and then you have lambda T. Okay, so if lambda, now you note here, lambda is the average number of outcomes per unit time and we are interested in small t interval. Okay, so your parameter will be lambda T. Sometimes people will call mu is equal to lambda T and then they'll write mu here. So that is the same thing, right? So this is equal to, without proof, this will be e raised to power minus lambda T raised to power X upon X factorial. Okay, so this is the PDF for the Poisson random variable, and Poisson random variable PDF is denoted by a small p, and then we define CDF, that is the cumulative density function, distribution function in this case, because we are talking about discrete random variable, that will be denoted by capital P X comma lambda T. That will be we will change this X here. Let us say we are counting till R, so that will be sum from X is equal to 0 to R of these PDFs, because you know that CDF is sum of PDFs. So this is how you have your CDF, and you will see that we have tables for capital P as well as small p also, right? So capital P tables are very useful, as we had the tables in binomial case. We do have tables for Poisson process also. And then okay, if you are interested in the proof of this, then you can just try looking for the proof, and if you have any doubts you can let me know. And then the mean and variance, but proof will not be a part of your examination. Mean and variance is equal to, for the Poisson random variable, mean and variance both are equal to lambda T. Okay, you can see that also, right? So mean will be, because obviously if lambda is the average number of like outcomes in unit time interval, then obviously what we expect in T time, we expect the mean should be lambda T, right? And why the variance is lambda T, that you can think of. And then also one more important thing, that when, note, that is very important, note that you can approximate a binomial process with a Poisson process when n is very large and p is very small. So np is a constant equals to mu. So you have a situation where np is equal to a constant mu. So we have a theorem that we can always, if this is the case, you can approximate your binomial process. This is how you write your binomial process, right? Okay, so when n is large, n goes to infinity, p is almost 0. In that case, you can replace it with the Poisson process x into mu, where mu is equal to np. Is that okay? So that is very useful, that because sometimes we want to discuss a binomial process with the help of a Poisson process, that you can do when your n is very large and p is very small. Okay, so this is everything which will be there in your exam regarding the Poisson process. So let us discuss one or two problems before we end this session. So let me write down the problem. Okay, so we have during a lab experiment, the average number of radioactive particles passing through a counter passing through a counter in 1 millisecond is 4 milliseconds is 4. What is the probability that 6 particles, what is the probability, is the probability that 6 particles will enter the counter in a given millisecond, will enter the counter in a given millisecond, in a given millisecond. So now you see here, so you are given that lambda is equal to 4, right? Because what is lambda? Lambda is number of particles per unit time, number of particles per millisecond. Okay, so here that is 4. And what is t? Because we are interested in a given millisecond, so that means t is also 1, therefore lambda t is 4 times 1, that is 4. Okay, yeah, so we are interested in knowing the probability that 6 particles will pass. So we are interested in probability that x is equal to 6 when your lambda t is 4. So that will be your e raised to power minus 4, that is, I told you this is the probability distribution, right? E raised to power minus 4, 4 raised to power 6, 4 raised to power 6 upon whatever is this number divided by 6 factorial. So you can compute it. This is 0.1042. Okay, let us do one more problem. So you have here 10 is the average number of oil tankers, is the average number of oil tankers, number of oil tankers arriving each day at a certain port, the facilities at the port, can handle at most 50 tankers, 15 tankers per day. Okay, what is the probability that on a given day tankers have to be turned away, Okay, so let us do it. So now you see, read the statement. 10 is an average number of oil tankers arriving per day. Okay, so lambda is 10. And then what is the time interval we are looking at? The facilities at the port can handle at most 15 tankers per day. So we are talking about per day again. What is the probability that on a given day the tankers have to be turned away? So you see, when the tankers will have to be turned away, when there are more than 15 tankers arriving at the port, because the port can handle at most 15 tankers. So we are looking at 1 day only. So t is 1, therefore lambda t is 10 times 1, that is 10. Okay, now we are looking for the probability that capital X, which is number of tankers arriving on a particular day, right? So we are looking what is the probability that capital X is greater than 15. So that is equal to 1 minus probability that capital X is less than is equal to 15. Now that will be 1 minus summation x from 0 to 15 of Poisson distribution x with the lambda is equal to 10. Lambda t equals to 10. So this is 1 minus capital P of 15 comma 10. Okay, you can see this from the table. So the table value is 0.9513. So that is 0.0487. So this is your answer. Okay. Now let us look at one more problem. So you have this problem that in a certain industry facilities, the probability that an accident will occur in a factory, let me write it like this, in a factory, the probability that an accident occurs on a given day, an accident occurs on a given day is 0.005, and accidents are independent of each other, and accidents are independent of each other. What is the probability that in any given day period of in any given period of 400 days? So the question is, what is the probability that in a period of 400 days there will be an accident on one day? There will be only one accident. Okay, so you see here, so you are looking at your lambda is basically your okay, so because here you have in terms of probabilities and accidents, so basically you have like this, you have day 1, day 2, day 3, day 4, and so on. So you have each day there can be an accident and there cannot be an accident. This is the situation. So the probability that there is one accident is 0.05, and we are looking at what is the probability that exactly one day the accident will occur. So basically this is a binomial process, but n is 400 and p is 0.005. P is very small, n is quite large, so np will be equal to 400 times a 0.005, which is equals to 2. Therefore this is a binomial process where we are looking at your n is 400 and p is 0.005. It can be approximated with the Poisson process with x and 2. 2 is your lambda, this is your lambda, okay, and 2 times 400, right, because we are looking at a period of 400. Okay, so that we have already multiplied, right, 0.005 and 400, so we'll write 2 here. So the answer will be e raised to power minus 2. Okay, so 2 raised to power, because we are looking at x is equal to 1, because we just want one accident, 2 raised to power 1 upon 1 factorial. So the answer will be 0.271. And then B part is, what is the probability that there are at most 3 days with an accident? What is the probability that there are at most 3 days with accidents? So basically we are looking for probability that x is less than or is equal to 3. So that is x from 0 to 3 Poisson x comma 2. So that is basically capital P 3 comma 2. You can see from the table its value is 0.857. So that's your answer. Okay students, so till now is the syllabus for your MST. So we finished our chapter 5, here. Okay, and that is your syllabus for your MST. All the best for your MSTs. Okay, bye bye.